Hi guys. Thanks for coming so far, everyone. We're just waiting for Professor Nassar to get here, and then we will get started. Hi, Professor Nassar. How are you? Yeah, if you want, Professor Nassar, we can just wait a couple more minutes for some more people to show up, and then, yeah, you can get started whenever you're ready. We're gonna record this event for those who are unable to make it.
Okay, can you hear me now?
Yeah, I can hear you.
Okay, so hello everyone, and sorry for being a bit late.
That's
Um,
okay.
Take my fast first, so you can join. Um, okay, so today is our second event about linear induction machine. So I'll start by taking some questions. Then we can talk about DQ modeling of electrical machines, because I think this is um, um, information that you need to know while you are doing control for your lamp. So I will just share my screen and we can start. Okay, let me know when you see my screen.
I can see it.
Okay, so I will start by taking your questions first, then we can continue. So, is there any questions you have? Is there any questions, any specific questions related to our previous meeting?
Um, I have a question.
Yeah, go ahead. Yeah, go ahead. Go ahead.
Yeah. So what we currently have a linear induction motor. It's just never has been tested. So it's laminated. It's isolated between each lamination, and we have three coils. The thing is that we still haven't been able to properly model the thermal profile of the limb. So I was wondering if it would be safe to push forward some tests before getting that simulation in.
Okay. So let's say this is your limb. Okay, you have your three coils. Okay, and let's say you are connecting them star. Okay, so here are the terminals. This is A, this is B, this is C, and this is a neutral wire. So you can start doing some um, safety testing before you energize it. So you can measure the resistance between A and neutral. Then you can measure the resistance between using an ohm meter, using a normal ohm meter. You can measure the resistance between A and neutral. Then you can use the same ohm meter to measure the resistance between B and neutral, and then C and neutral. Okay. If you see a resistance between them, it means that the insulation is fine. There is no short circuit internally. So you can test the insulation by testing a resistance. Then you measure the resistance between AB, BC, and CA, also to make sure that there is no hidden short circuit that you didn't catch. And after this, you can start energizing. And when you start energizing, you can start energizing with low voltage and then increase the voltage slightly. And while you are doing this, you need an ammeter. So let's say this is a coil A. I will energize this coil A and see if it is working fine. So I will have a variable source and they will have an ammeter here. So you know what is the wire gauge you used, correct?
Yes, I don't have it by hand right now, but
No,
it's
no. Yeah, just I'm saying you know it. So you know what is I maximum that it can
okay.
carry. Yeah, so you keep increasing the voltage. If you reach it V rated and the current is still less or equal I capacity of the wire, okay, it means that this phase is okay. Okay. And you can do this without thermal analysis. You can repeat this for phase B and you can repeat this for phase C. This is like an initial safety test before you energize.
Okay, perfect. I was also wondering if what would be like an option for low voltage applications, like for these ones, because we're also working on an inverter, although it's still not fully ready. So we wanted to like test both the limb and the inverter like on parallel. Like a different team will work on the limb. Um, but yeah,
So
we didn't
do,
have
do,
like any low voltage source. Yeah, sorry.
do you have a low voltage variable source in your lab that you can use to that can supply a variable AC?
Yeah, but they're very low power output, if I remember well. I think it would be in the range of like maybe like 50 watts or 100 watts
And
tops.
what you need? What
Uh,
is the power of the limb?
for now, we still haven't determined that because we have to see with the weight of the whole entire capsule. But this is like a limb we're preparing for the next competition, on this one that's going in 2023. So right now, I was just like wondering if that would be enough for like some initial tests, like you said.
Okay, so let's say this is a track here, okay, and this is your limb, and you are energizing the limb from the source, okay. So this source is feeding two types of power, okay. It feeds power for the limb itself, which is losses, and this losses is iron loss and copper loss, and it feeds some other power that will go to mechanical power that will propel the limb, okay. So if we say that our limb is um, 15 or say 800 watt, I don't need a source 800 watt to test this limb at no load, because this testing is no load testing. No load means we don't have this mechanical power. Now let's estimate that our efficiency for the limb is 80%. Okay, let's say this is an assumption, which means we have 20% losses from the total power. And this 20% losses will be zero point 0.2 multiplied by 800, which means we will take 160 watt to supply our limb. So we need a supply roughly 160 watt. We don't need the full power source to supply the limb, the testing of the limb, because we are testing at no load. Just we need to supply the iron and copper losses.
Okay, that makes sense. Thank you.
You will. And for inverter, um, so you are getting a VFD.
We have an VFD at the shop. The thing is that there's some problems with the electrical state of the shop itself, so we can't use the VFD right now. So we're using I don't know what's the type of the inverter, but it's a mountable one on that we could use on the capsule. It's a Bamukar, if I'm not mistaken.
Okay. But which one you are going to use in your competition, in the competition? So are you
Yeah,
going to
it's
the VFD?
no, it would be the Bamukar.
Okay. So you know what is the rating of it?
Yeah, it's I believe it's just gonna double check. It's 160 kwatts.
160 kilowatt.
Yeah, exactly.
Yeah, this is so powerful. Yeah, so powerful.
Yeah.
It's so powerful.
Yeah, would you recommend to keep working on with that inverter since we have it, or to like change for a less powerful one?
Uh, so for this iteration, you can keep working with it, but I never recommend it for students to build their own inverter, because this is like um, a challenge by itself. It will take too long until you tune the filters and adjust the control. So I recommend using an over-the-shelf inverter. Uh, Larger inverters are good. You are not loading it that much, but also because they are powerful. If there's a short circuit, they will push large current through the circuit. So you have to be careful about adjusting the current limit. So the good point about inverters, they have current limiters. So make sure you are configuring the current limiter. Okay, and
Okay,
configure the
perfect.
current limiter to be 25% over the ampacity. Okay, so let's say that the wire gauge you are using um, can carry 20 ampere. So you will rate it as 1.25 multiplied by 20, which is 25 ampere. So you will adjust the current limiter to limit the current to 25 ampere. In this case, even if you have a short circuit, the good point about VFDs is that they can limit the current. And also, um, let's say here are our three phases that will be going into the inverter. I would add a fuse here in this connection. These are fuses. And also fuse, you can increase it by 20% or 25%. So if your motor can take current 20 ampere, you can take a 25 ampere fuse. In this case, for any short circuit, the fuse will damage and it will you will protect your limb coils. And this will be like a second line of defense. So this is a backup for the current limiter.
Yeah, that makes sense. Thank you.
You're welcome. Okay, is there any other questions from students attending? Is there any other questions? Okay, should I move with the DQ modeling and DQ control? Should I move or you have questions?
I think you're good to get started.
Okay, that's good. Okay, let's talk about DQ. Okay, DQ. Anyone knows what is the DQ? What is the difference between ABC and DQ frames? Okay, let me explain this. So if you look at and we will take the um, induction machine, the normal induction machine, as a base case, then we can move. So if we look at the induction machine, okay, or any AC machine, let's name this as an AC machine, because induction and synchronous are similar in terms of their stator part. And this machine is three phase, so it has phase A, phase B, and phase C. Phase A, phase B, phase C. And these three phases are rotating with time. So if you look in time, so there will be rotating, okay? And the rotation speed or the rotating speed is the rotating speed omega synchronous is 2 pi f synchronous rad per second. Um, and this was the okay, sorry. Let's explain this in details. So case one, case two. So case one, we can have this three phase and supply this three phase with a DC current. So we have a current here IDC, we have a current here IDC, we have a current here IDC, and the three here are rotating with a speed omega s. So if we have this, we will be creating a rotating magnetic field. So to create a rotating magnetic field, we can have set of coils, we supply them with DC current, then we rotate the whole set. We have to rotate this with omega s, which means our coils has to be moving coils or rotating coils. Now, what is the issue with moving coils or rotating coils? To keep contact with rotating coils, we will need to use brushes. And a good example of this, if you look at the uh, electric trains, the light rail trains, LRT. So LRT is an electric train, and we need to supply this LRT with current, with electricity. We cannot connect it to a supply directly. So what we do, we will use a brush, and this brush will be touching the overhead line. So while the light rail train is moving, it will keep contact with the line. So while it is moving, it's still keeping contact with the line. And this is a sliding brush. Sliding brush. So to keep contact with a moving coil, we will need brush. Okay? And this brush is a deal breaker, because this brush will increase losses, will create heat, will have a sparking. It will need a lot of maintenance because you need to change it over time. So we need to try to have this motor as brushless. To come with a brushless motor, Tesla came with the following idea. He said, okay, instead of rotating the three phase, let's supply the first phase with a source VA, the second phase with a source VB, the third with a source VC, and let's keep these three sources as AC. So this is V angle 0, V angle minus 120, V angle positive 120. In this case, you will create a rotating magnetic field. The magnetic field will be rotating with a speed omega s, while the coils are stationary. And this is a breakthrough that Tesla did. He was able to generate a rotating flux from stationary coils, which means that this machine is not rotating. So the machine itself is not rotating, while the flux produced by the machine is rotating. And he did this by using three phase shifted by 120 degree. In this case, if we look at the machine, because the machine is not rotating, here we can have a solid connection. No brushes, no brushes. That's why the machine is brushless. Okay, so the machine is brushless. There is no need for brushes, which means that in AC machines, in AC machine, the machine itself is constructed from three phase coils A, B, C. Phase A, phase B, and phase C. And the current in them, IA, IB, IC, IA and IB and IC are AC currents. Okay? Which means if we look at the currents versus time, we will have a sine wave for IA, sine wave for IB, and sine wave for IC. Okay? Does this make sense so far?
Yes.
Now let's go to the issue we will have with this. Okay? Let's say we have a motor here, and this motor has three terminals, A, B, C, and we need to control the motor. Okay? To control the motor, we will need to set IA, which we will call it as IA reference, and we will need to set IB, which we will call it as IB reference. I will need to set IC, which we'll call it IC reference. So to control the machine, we will give the machine a reference to follow. Okay? And the machine will try to follow the reference by calculating the error between the reference and the actual value, and feed this error, say, to BID controller, and drive the machine with this BID controller. So if we have a reference value, we compare it with the actual value, we feed this to a PID controller. This will give us the control signal that we will feed it to the system or the machine. Then we will take a feedback or measurements. This is measurements or feedback. So this PID controller will have an error steady state equal 0. This is by design. So the PID controller will give you a steady state error 0, which means versus time, if this is a reference value, the actual value will follow the reference value. The error will be 0 at steady state, but it can follow the actual the reference value will follow, or the actual value will follow the reference value following an over damped response, or a critically damped response, or an under damped response. And which one the actual value will be, it depends on the parameters. So this will be depending on the PID values or the PID tuning. You can have an over damped response or an under damped response. Most of the cases will be an under damped response, because the under damped is a bit fast. But the issue with under damped response, that you will have what is called an overshoot. You will have overshoot here. So adjusting the PID controller will adjust the settling time, the overshoot, and will adjust the damping ratio, etc. So you can adjust these values through the PID control. Now, as you can see, we sketched the reference value as constant. Okay, it's a constant value. Now, what is the reference value in our case here? So the reference value in our case here cannot be a constant, because IA is sine wave, IB is sine wave, IC is sine wave, which means that IA reference has to be a sine wave. So we need our system to track an AC sinusoidal reference. Okay, and this is impossible. Okay, you cannot track a sine wave. Okay? Anyone studied this in control? Anyone studied this kind of reference and step response in control? So
I've seen some documents talking about it, but I don't really understand the mechanics behind it.
yeah, okay, that's good. Okay, so we can give it a little more detail. So we have this type of reference. The reference can be constant, or the reference can be linear, or the reference can be a sine wave. Okay, so this is type, first type, second type, third type. We can design our control to follow a reference. This is the easy one. Okay, because your reference is constant. Constant means it's a type 0. So you need an first order system to follow it, or a second order system, it will follow it with 0 error. For type 1, which is this linear reference here, you will need a type 2 to follow it, or type 3 to follow it with 0 error. For sinusoidal, you will need an N type, maybe type 4 or 5 to follow it. And this type means what is the order of your transfer function. Your transfer function, it will have an order N here, and this order is called type. So type 0 means N equals 0. Type 1 means N equal 1, and so on. As the type goes higher, type 1, type 2, type 3, as your system getting slower. Type 2 is slower than type 1. Type 3 is slower than type 2. So if we can follow the reference with a lower type in our system, it means that our system is faster. That's why we don't recommend to have any one of these references, because to follow these references, we will need a higher type system, and the higher type system means the system will be slow. That's why we will try to keep our reference as a constant value. To give you an idea, let's say we have a robot arm, and this robot arm is tracking a point. Okay. The first type means that this point is stationary in space. So I'm telling my robot, follow this point. Okay. And this point is at, if this is 0, is at -5 and +3. So we will tell our robot, follow -5, 3. Okay, this is our X value, this is our Y value. So your robot can move until you go to -5 and 3. So your robot can go in the space, then stop here. It can do some overshooting. It can go past the point and then go back, or it can go very slow to the point, depend on the response. However, what if we are telling our robot to follow this point, and this follow point is moving, is moving, okay? Let's say it is moving linearly, okay? So it's moving on a straight line linear, okay? So it is moving linearly. Is it easier to follow this for your robot to catch this point while the point is following linearly, or is it easier to catch this point while it is stationary? Which one is easy in tracking?
The stationary one.
Yeah, compare this to it is oscillating following a sine wave. Compare this even to line, to straight line. So if you rank them from easy simple to the harder, so the easy one will be a fixed point or a constant reference. Second one will be a linear reference. Third one will be a sinusoidal or a parabolic reference. Does this make sense? Why we are trying to keep our reference as a constant value versus time? So it's easy to track. We can reach this reference value with a zero steady state error. Does this make sense?
Yes, sir.
Now, if we go back to our motor, okay, and we try to control the three currents IA, IB, IC, in this case, our reference here has to be a current. It has to be a sine wave, okay? And we cannot do this, okay? This is very hard to do. So they came up with an idea, okay? And this idea is based on magnetic equivalence. They said, okay, what is the three coils are doing? So we are supplying three coils with IA, IB, IC, and the three coils will be generating a flux phi, and this flux phi is rotating in space with a speed omega s. They said, okay, let's do the following. Let's take, instead of three coils, let's assume that our machine has two coils, just two coils. And these two coils are fixed. We can call these two coils as alpha beta. Okay. So if we sketch the directions, this is A, B, C as vectors. Let's give them an angle. Okay. So they have an angle with the x-axis. Okay. So this is the ABC. We call it the ABC frame. So in the ABC frame, we have three phases shifted by 120 degree. Okay, and we have three coils. Now we will move to another frame where we have two coils or two directions. The x direction, we call it alpha, and the y direction, we will call it beta. And these directions are fixed in space. Okay, we will call this the alpha beta frame. Okay, now what we are supplying these two coils, we will supply these two coils with I alpha and I beta, and the angle between I alpha and I beta is 90 degree. Okay, this is a two-phase machine, and this is a three-phase machine. And we can adjust the number of coils in alpha and the number of coils in beta and the current I alpha and I beta. So we are generating the exact same flux phi that is rotating with the exact same speed omega s. So we can find a relation between the number of turns in A and the number of turns in alpha and the current IA and the current I alpha. So there is a magnetic equivalence, which means we can sketch this circuit here, which has two phase, in equivalent to the circuit with three phase. And the two circuits are producing the exact same flux. And if they are producing the exact same flux, they will produce the exact same mechanical power and all the characteristic later on. Okay? Does this make sense?
Yes, sir.
Now, still the issue here that the currents here, IA and IB, IA and MB are sine waves, but these sine waves are shifted by 90 degree. Here we have sine waves, but these sine waves are shifted by 120 degree. Okay, so still we didn't solve the issue completely. Still we have But instead of we have 3-phase currents, we have 2-phase currents. So we simplified the problem a little bit, but still the problem is still there. Then they said, okay, let's do the following. Let's take these 2 coils and move them, rotate them with a speed omega s. And they are producing the exact same flux, phi. Now, the whole frame or the whole axis, your axes themselves, the axes themselves, they are rotating, okay? And they are rotating with omega s. If your axis rotating with omega s, what is the rotating speed of the flux?
Omega s.
Yes. Now, what will be this current here? Is this current will be AC or DC? So AC, you are creating a rotating flux from a fixed coils. DC, you are creating a fixed flux. Now, is our current here AC or DC? Don't forget that the coil itself is rotating. So we don't need the flux to be rotating. We need just the flux to get a value. And we are rotating it by the rotation of the coils. In this case, the 2 currents will be DC. So here, the currents will be DC. And they will name this as D, and they will name this as Q. And this current will be ID, and this current will be IQ. And they will call this the DQ frame. Okay, so in the DQ frame, we will have our D direction and our Q direction. But the difference here is that these 2 axes are rotating with omega s. They are not fixed in space. And we will call this the DQ frame. Okay, clear what is a DQ frame is? Any questions so far? Any questions so far? We are good to move. We are good to move.
Yes, sir.
Okay, now how we do the transformation? Okay, so now we transfer ABC. We start by transferring ABC. We transfer this to alpha beta. Then we transfer alpha beta to DQ. Okay, this is a transformation we have. Okay, so we have a transformation ABC. Then we have a transformation to alpha beta. Then we have another transformation to DQ. So how we can get this transformation? So transformation from ABC is easy. It's just um, angles. Okay, so you have an angle theta here. So to convert A to alpha, you will take cos theta. To transfer B to alpha, you will take cos 120 minus theta, and so on. If we align, let's take ABC to alpha beta. Okay, so here is A, here is B, here is C, here is alpha, here is beta. Okay, now how we do the transformation from ABC to alpha beta? At the end, it's a flux. I need the flux generated here to be the same flux generated here in terms of magnitude and direction, which means if I have a current here, I will find its projection in alpha direction and beta direction. Okay, so if we say this is alpha direction, here is beta direction, this is IA. Now, what is the component of IA in the alpha direction? What is I alpha in terms of IA? It's IA, correct? What is I beta in terms of IA? What is the component of IA in the direction of beta? Hello.
I would say the projection of B onto the alpha, so it would be cos angle.
Yes, it's 0 because the angle is
Yeah.
90.
Yeah.
Okay, then we will take IB. here is IB, and this angle is 120. So this angle is 60, okay, and this angle is 30. So the current IB in the beta direction will be IB cos 30. The current here in this direction will be IB cos 60. And this one is negative because it's a negative beta, and this one is negative, correct? So if we find what is I alpha will be 1 multiplied by IA plus or minus cos 60. What is cos 60? Is the root 3 over 2 or root 2 over 3? It is root 2 over 3 IB. And also if we have IC here, this angle will be 30, this angle will be 60. So this is plus IC multiplied by cos 30. And this is cos 60. And here I beta will equal to IA is multiplied by 0, IB is multiplied by cos 30, and IC is multiplied by cos 30 IC, and this one is sine 30. Okay. Now we can get I alpha and I beta as a matrix form of IA, IB, IC. This is 1 minus cos 60 sine 30, 0 minus cos 30 cos 30. Okay. And this is sine 30. Okay. So this will be the transformation matrix. This is a transformation matrix. Does this make sense so far?
Yes, it does.
Now, what is the issue with this transformation? If you have IABC, you can move to alpha beta by multiplying it by this matrix. What if you have alpha beta? What if I have I alpha, I beta, and I need to find what is IA, IB, IC? What I should use here? So here we have I alpha, I beta equal this transformation matrix multiplied by IA, IB, IC. This is a transformation matrix we have, which is this matrix here. What if we need to do the opposite? We need to get IABC as function of alpha beta. What we need to do here?
I would say take the inverse of the transformation.
Yeah, what is
matrix?
the inverse of this transformation? So what is the size of the transformation here? It's a 2 by 3. Okay. Can you inverse a matrix that is not a square?
No.
So which means that we cannot go back to this. We don't have the inverse transformation. We don't have the inverse transformation. So how you can solve this? How is he solving this? Any solution here? Do you see what is the issue here? So we can move from ABC domain to alpha beta by using the projections. By using the projections, we can convert the ABC to alpha beta. And the matrix we have is 2 by 3 matrix, which means if I have the ABC frame, I have IA, I have IB, IC, I can get I alpha, I beta. However, if I have I alpha, I beta, I cannot get IA, IB, IC. Why? Because I will need the transformation inverse, and the transformation matrix is 2 by 3. I cannot find an inverse for it. So how we can solve this issue? So we need to make this matrix 3 by 3, correct? IA, IB, IC. Here we have 1. And what is cos 60? I think cos 60 is, let me calculate this or find this. Farida. So cos 60 is negative 1 over 2. Sine 30 is negative 1 over 2. Then we have 0. We have root 3 over 2, negative root 3 over 2. Okay. This is the transformation matrix so far. Now, what we will have here, okay? So we are adding a third line here. Here is I alpha, I beta. So we need to add a third element here. In this case, our transformation matrix will be 3 by 3. And also we need this third element not to change our flux. So what is a fact that we can add here? We need a third equation to add, a third variable here. So we have this matrix 3 by 3, so we can find its inverse. And at the same time, we don't need to change the information we have from the equations. So how we can do this? Any idea how we are going to do this?
I would put 0 there, maybe.
What if I added 1, 1, 1? What we get? 1 IA plus 1 IB plus 1 IC, correct? What is this current is? So if I added 1, 1, 1, so I'm getting here IA plus IB plus IC, which is I neutral, and I neutral is always 0. So adding this third line here will not change our equations, but it will allow us to be able to do the inverse. Does this make sense?
Yes, sir.
So now we have our alpha beta 0, they call it alpha beta 0, okay, will equal to transpose because it's a vector, will equal to this matrix 1, negative 1 over 2, negative 1 over 2, 0, root 3 over 2, negative root 3 over 2, 1, 1, 1, multiplied by ABC transpose. So this is a relation between ABC and alpha beta. However, this transformation, I don't want to go into details. It's a power variant. It will change the power. To keep it power invariant, we can do a proof that we need to multiply it by root 2 over 3. So this coefficient or this constant to make the transformation power invariant, which means that the power you will calculate from alpha beta is the same power you you calculate from ABC. Without this root 2 over 3, it's a flux invariant. It will not change the flux. You are getting the same flux. However, when we multiply the transformation by this root 2 over 3, it will be power invariant. Okay? Does this make sense so far?
Yes, sir.
And this will be the transformation matrix, and this transformation matrix is constant. So the transformation matrix that will move us from ABC to alpha beta 0 is 1, 0, 1, negative 1 over 2, root 3 over 2, 1, negative 1 over 2, negative root over 2, 3 over 2, 1. This is the transformation matrix. And it is multiplied here by root 2 over 3. And if we take the transformation inverse, this will move us from alpha beta 0 to ABC. Okay? Now, what will be the next? The next will be moving from alpha beta 0 to DQ. Okay? So how we will do this move? So the idea is we are moving from ABC to DQ, but we cannot move from ABC to DQ direct. So we will move first to alpha beta 0, then we will move from alpha beta 0 to DQ. So how we will do this transformation from ABC, from alpha beta. So this transformation is the one we calculated, root 2 over 3, 1, 0, 1, negative 1 over 2, root 3 over 2, 1, negative 1 over 2, negative root 3 over 2, 1. Now, how we do this transformation from alpha beta 0 to DQ? So here is alpha direction, here is beta direction. And these directions are fixed in space. This is stationary, and this is stationary. The difference between them and DQ, that the DQ, they have 90 degrees in between, but they are rotating with the speed omega s. So how we can do the transformation? So let's take this here and add it here. Okay, and let's take an arbitrary point where these are moved with an angle theta. Okay, so because D and Q are rotating, so we will take them making an angle theta, and we will do the same. Okay, so what is the same? We can say that I alpha equals to ID cos theta. It's like the projection of ID here. ID cos theta will be I alpha. And then IQ, if this is theta, this will be theta. So IQ sine theta will be in this direction, IQ sine theta. But it is in negative alpha direction. So this will be minus IQ sine theta. Then I beta will equal to, here we have IQ cos theta, IQ, or sorry, ID sine theta. This is ID sine theta, and this is IQ cos theta. So it will be ID sine theta plus IQ cos theta. And this will be the relation between alpha, beta, and DQ. Does this make sense?
Yes, sir.
So in this case, we can say that alpha, I alpha, I beta equals cos theta, sine theta with minus, sine theta, cos theta, multiplied by ID, IQ. Okay? Make sense? Make sense so far?
Yes, sir.
Now, what if we need to calculate IA, IB, IC as function of ID, IQ? In this case, we will move from ABC to alpha beta. So the transformation is root 2 over 3. Then we have 1, 0, 1, I think, minus 1 over 2, root 3 over 2, 1, minus 1 over 2, minus root 3 over 2, 1. So this will be multiplied by I alpha, I beta. Then I can remove I alpha, I beta, and I can add cos theta minus sine theta, sine theta, cos theta. Okay, but what is the issue now? The issue is this matrix 3 by 3. So I need this matrix to be 3 by 3. So what we will do, we will add I0 here. We'll say 0, 0, 1, 0, 0, 1, which means I added I0 here, which is the same as I0 here. So here we have 0, 0, 0, 0, 1. So we added the neutral current in both, in DQ and alpha beta. And we say that the zero current in alpha beta is the same as the zero current in DQ. So this equation is I0 equal to I0. So here we have 0 ID plus 0 IQ. So here we have 0 I0, here we have 0 I0. So this will be the three equations we have. Now we can multiply these two equations together, and this will give us the transformation that will move us from ABC to DQ0. Okay? And this transformation is called the Park transformation. So the Park transformation will equal to root 2 over 3 multiplied by, where is let me bring the final answer here. So DQ, this is will convert the DQ0 to ABC. So we have 2 over 3 cos theta cos theta minus 120, cos theta plus 120, sin theta minus 120, sin theta plus 120. Okay, and we can say this will be 1, 1, 1, and this will give us a dq0 function of ABC. Okay, and we can find the inverse transformation to be cos theta minus 120, sin theta minus 2 pi over 3 is 120, cos theta plus 120, sin theta plus 120. So this is the transformation that will move from ABC to dq0. Okay, now what is the importance of this transformation? Okay, now let's take this into application. What is the importance of this? Let's say we have a motor here. This is three-phase induction machine, and it is supplied from three-phase ABC, and we can measure the currents using current sensor. Okay, so this will measure IA, this will measure IB, and this will measure IC. Okay, now instead of doing the control using these currents, in this case I need IA reference to be sine wave, IB reference to be sine wave, IC reference to be sine wave. We are not doing this. What we will do, we will use the transformation we have, the ABC transformation into dq0. So this will give me what is ID and what is IQ in the machine, the equivalent ID and the equivalent IQ. And don't forget that this ID will be DC and this IQ will be DC if IBA is AC, IB is AC, and IC is AC. Make sense what we are trying to do here? And this will be the transformations that we found. Make sense what we are trying to do here? So we will measure IA, IB, IC, which is three-phase sinusoidal. We will apply the transformation equation, and this is numerical. You can have this on your control, on your DSP or whatever controller you are using. You will multiply IA, IBC with the transformation. You will get ID and IQ. In this case, ID and IQ are fixed. They are DC. So I can add a comparator here with ID reference, and the ID reference is fixed. It's a constant value. So we are tracking a constant reference. And here I can add IQ reference. So this will give me error in ID, and this will give me error in IQ. Okay, I can apply this to a PID controller or PI controller, which will give me what I need as VD and what I need as VQ. Then I can use this as the inverse transformation, the DQ to ABC, which will give me V reference A, V reference B, and V reference C. Just 1 second. Okay. So this can give us the voltage references, which is the three-phase voltage reference. We can use this to control our inverter, which controls the machine. And we have equations that relate ID and IQ to the torque and speed of the machine. So we can translate the torque reference to ID reference, and then use this ID reference to compare it with ID and get the error using a PI controller. And we can set IQ reference as 0. In this case, our ID reference will be generated from the torque, and IQ reference will be set as 0. And there's many ways to do the DQ control. Once we have the DQ model, we can do different alternatives for the control. Make sense so far?
Yes. Although I had a question. So in your model, since we're measuring the current through ABC, does that mean that ID and IQ are not constant but updated every continuously? Is that or
Yeah. They are updated continuously.
okay? That makes sense. Okay, thank
Yeah,
you.
but they are still. So if your AC RMS didn't change, IDC shouldn't change. So for the same sine wave, okay, A, B, C sine waves, if this RMS value or the peak is didn't change, your ID and IQ will be constant. So it is updated each sample. It is updated, but it still is constant. What will change its value once this sine wave start to change? In this case, your value will increase. So it is constant as far as your AC current didn't change.
Okay, that makes sense. Thank you.
Any questions so far? Any questions so far? So we can have another meeting. We can continue with, once we know what is a DQ model, what is a DQ transformation, the Park and Clark transformation, we can start looking into control different control techniques. So we can look at block diagrams of different control for induction machine. Okay, we can do this next time. Just I need you today to get an idea about what is the DQ transformation, what is its importance, what is the difference between alpha beta frame and DQ frame, ABC frame, and how we can move between them.
Awesome. Thank you so much, Professor Nassar. That was great. I'm sure a lot of these students found it very helpful, and we're going to send out the recording to the others who were able to make it as well. I really appreciate you taking the time out of your schedule to come and do this for us, and we would definitely love to have you back again for a third installment of this sort of event. So I'll definitely reach out to you. We can coordinate that.
Yeah.
Is there any final questions for Professor Nassar? Anybody? No? Okay, awesome. I also want to give a little shout out to Dr. Ryan Jansen of Transpod, who's joined the call as well, to look in at one of our events. So I'm glad you're here, Dr. Jansen. That's awesome to have you. But yeah, thank you everybody for coming. If you have any questions, feel free to stick around. Or if you have questions about the upcoming conference, I would be more than happy to answer as well. But thank you so much everybody for coming. How are you, Dr. Jansen? Oh, I can't hear you. I don't know if your mic is not working or something. Yes? Awesome. Good. Good.
Okay. Thank you all for joining today. Thank you, Dr. Ryan, for joining. Nice to meet you. And yeah, see you in the next meeting. We will go through some control block diagrams for induction machines.
Awesome. Yeah. Thanks again, Professor Nassar. I really, really appreciate it.
Thank you. Okay. Bye for now.
Bye.